Good morning. This is Dr. Rajkumar Arya, Associate Professor in Department of Chemical Engineering, IIT Jalandhar. Today I am going to explain heat transfer in a plane wall. So this is a plane wall. We are considering first heat transfer only in x directions. So we have taken a differential segment of delta x thickness. So the heat, this is energy in at x, energy out at x plus delta x, thickness is delta x. Now area of this is the uniform, is not changing with respect to x coordinate. So area perpendicular to the direction of heat flow is ax plus delta x equal to a, which is constant. Energy is being generated within the material, so E dot generation is also there, and entire thickness of the wall is L. So this is simple statement for that. Consider a thin element of delta x in a plane large wall. Density of wall dense rho, specific heat C, area of wall normal to direction of heat transfer A. Okay, so energy balance for differential delta time, rate of heat conduction at x minus rate of heat conduction at x plus delta x plus rate of heat generation inside the element equal to rate of change of energy content of the element. So that q dot x minus q dot x plus delta x plus E dot generation of the element equal to delta E element upon delta T. So delta E of element is given by this rho Ca delta x T plus delta T minus Tx. So A into delta x can give you the means volume of the material, so differential element actually. So E dot generation is given by E dot generation A delta x. Substitute all of them in governing equation. There we have delta x qx minus qx plus delta x plus E dot generation A delta x rho Ca delta x T at time t plus delta t minus t at time t upon delta t. So here dividing by this equation by A delta x, substituting the limit delta x tends to 0, delta t tends to 0, you will end up with 1 upon A del upon del x Ka del t upon del x plus E dot generation equal to rho Cp, and we have taken the Fourier's law of heat conduction also there, that Q equal to minus Ka delta t upon del x in this particular equation here. So there you have this one, so dq upon this. So since A is constant for plane wall, so you have this one del upon del x K del t upon del x E dot generation equal to rho C del t upon del t for variable conductivity. Most practical application, thermal conductivity is constant, so K del square T upon del x square. E dot generation equal to rho C del T upon del T. So for constant thermal conductivity, we will get the relationship here, there's alpha here. So alpha is thermal diffusivity of the material and represent how fast heat propagates through a materials. So for steady state operations, there you will get d square t upon dx square plus E dot generation upon k equal to 0. For unsteady state with no heat generations, that del square t upon del x square equal to 1 upon alpha del t upon del t. For steady state, no heat generations, you will end up with these equations all the time, d square t upon dx square equal to 0. So this is second order partial differential equation. Total differential equation need two boundary conditions to solve all the time. So these are references. One is heat and mass transfer, fundamentals and applications. Other one, heat and mass transfer, a practical approach. So thank you very much. In case of suggestions or doubt, you can drop your comments.